usually actually tell you about the rows and some of the samples of the data set just for you to visually get a feel of what's happening. Although I usually prefer to write the data set as it is because this just gives me more information. But yeah, this is how we realize that how much data do we have? Is it even quantifiable for the task we are going to do? And should we even proceed with this or not? Should our first concern be that, hey, let's gather more data or let's have more columns? Like this data does not look to be good enough for us to even think about modeling that will a person leave or not. That's the second thing. That's the first thing. Another thing is look at the columns. When you look at the columns, you realize some columns are some things which you would not get in your actual data set. I mean, the data you have is because you just took out some of the data from your maybe your logs, system logs, or maybe from an HR department, and they have these fields called exit reason and exit comment. But think about a person who you want to predict that is that person going to leave or not. You won't have the exit reason and exit comment field, right? So this particular kind of these two columns is what I can see are becoming a bit of redundant. So this is called target leakage. So if someone has given an exit reason, they would have obviously left, right? So we cannot use exit reason to actually model the part that they have left or not. So this is what a basic loop gives you in general. Another thing which I like is the info methods of pandas, which actually tells us what are the data types of these particular columns in general. Objects are something which Python uses for anything which can be represented in a string format. So it can be a JSON string, it can be a list, anything like that. Integers are something which actually tells me that, hey, these are numbers, we can do operations over them. So ints and floats are something where you actually start realizing that, hey, these are numerical columns. We can actually plot the distributions. We can actually see how they are distributed. We can just get a visual vibe of the data set. Another thing which I like is describe, but I like it with include all parameters in general. So this gives us a good amount of descriptive statistics. So you can see for the employee ID, you would expect it to be a unique field because why would two people share same employee ID? There's no reason to. But this is where we see that, hey, only 2,000 of them are unique. So there is a good chance that there is duplication or contamination in our data set. That maybe if we were asking surveys via a form, so maybe the form was doubly filled by a person, or maybe we were processing the data and someone messed up really bad and a couple of entities get duplicated. That's the part where this particular kind of analysis matters. It just gives you a visual overview of what's going around. You can see that, hey, engineering department is the department which has most amount of people and its frequency, which is 790. There are a lot of plans, but you can practically ignore them because you always realize that, hey, most often than not, these are there when they are not needed. Like there is no need for, I would say, unique in salary because there are too many variables in general. Like why would you want to plot unique? So this is very smart in itself. This is just a more robust way of finding out just what kind of particular information you want. You actually want to see that what was the percentage of unique data points in general. Like here, 99.6% of data points are unique. So we won't really say that data is completely contaminated. I would say there are just a few rows and columns. We should just maybe weed them out, inspect them, what went wrong over there. But we shouldn't just throw it away in general. Obviously, join dates are pretty unique as well. But you can see there is very less, I would say, unique ages. So obviously, we know that we are going to have ages in a certain interval. And what this 38 gives me an idea is that maybe it's from 22 to 60. Like that's just a feel of the data that, hey, this is we are going with the data like this in general. Now we know there are 9 departments, and the satisfaction, which we can also plot by different ways, tells us that maybe it's a scale of 1 to 5. That's where there are like 5 unique values. So this is why you should actually try and analyze the patterns in the data manually so that you can get a better feel of what kind of model you might be using or what kind of analysis you might be presenting in general. So forget machine learning. A simple model I could go for is that, hey, let's just say people who are on the satisfaction of 4 or 5 are not likely to leave. And people who are below it are more likely to leave. That's just a simple prediction from my end without using any machine learning model. So in this particular sense, what you would want is that, hey, is my model going to be better than this naive prediction? Like a person who just comes up and says, yeah, let's just have this very naive model that, hey, if a person is satisfied, they're not going to leave. Am I going to do something which is going to be significantly better than that? Is my effort even justified? That should I even go there and do this thing, work for hours, and then come up with something like that? If I'm predicting via accuracy, I would like to see what accuracy do I get with these naive models in general. And if the accuracy is good enough, I don't think there's a need for machine learning in a lot of problems. But if the accuracy is bad, and I realize that, hey, a machine learning algorithm can improve it, and it does improve it, I can actually justify the gain and my time spent on that particular thing. That is why getting the hang of data is very important. It kind of helps you make naive decisions, like how a person just looking at the data would say, yeah, let's do this in general. So this is how I like to plot missingness in general. I also like to classify every column into a type of feature in general. So employee ID is a string, and I know it's a feature of ID, but there's features like age, tenure, salary. These are continuous features. There's no restriction saying that, hey, age has to be between 20 to 30. In this particular area, we do realize that, hey, age is just a number in general. It's not a range. So these are very continuous features. There are some features which are ordinal, like job level. So clearly L4 level is going to be greater than L3 level. It's a better level. So obviously the order matters over here. You can't really interchange the order of L4 and L3 and say that, yeah, they are the same things in general. So these are the ordinal variables, but departments is something which is nominal. There is no ordering. You can't really say engineering department is greater than design department or HR department. So that's a nominal feature. So you actually try to see that what kind of features do you have, and did the person leave or not? That's called a target in our particular case. We also need to see that is the target binary or multi-class or a numerical target or an ordinal target. This is a binary in this case, whether the person left or not. And this is imbalanced also because I wouldn't want it to be balanced. I wouldn't like a company where half of the employees leave. So yeah, 75 to 25. Although it's bad, but still not that bad, I would say. So usually when you get the hang of it, you actually plot everything with a single function. You have your own notebooks, you have your own code, just to take a data set and just do everything. And now you have your good coding models as well, which can actually give you all of these information, can write the code for you. So this is why I'd say that thinking matters more, because you can give a prompt to your Claude or Gemini or ChatGPT and they will write you the code, but thinking is what actually matters in this particular sense. Now we start thinking about features. A lot of times when you have data in reality, you actually want to learn about features. What do they mean in general? Most often than not, you ask the business people that, hey, what does this mean? How was this data even collected? So that you can realize that, hey, if this is going wrong with the data, then the probable reason might be that data collection was not a good way of asking. Like, think about salary. Salary as a feature. You shouldn't really ask salary in a Google form when you are collecting data for employees, when you have the deterministic answer of salary in your own HR portal. Like, asking salary will obviously introduce errors. So this is when you start thinking about the features on how the data was collected, what kind of data is present, does the data even make sense? And that is usually done by analyzing the data even on a bit deeper level. You actually kind of go into more of a univariate analysis, that you analyze the feature one by one. So right now what we were doing was, we were actually seeing all of the features as a complete set. Like, hey, let's in a single function see what this features mean, what the other feature means. But now we are going to see them as an individual features, and this is what's called the univariate analysis. So again, we use the similar functions, but now we actually go into plotting as well. So let's talk about the most important feature in most of the cases in this data set, which is salary, because I think that says a lot about if a person wants to leave or not. So we would actually want to see the statistics of salary in general, like what's the average salary, what's the mean salary, what's the median salary. Median is usually given by 50% in general. What's the standard deviation, like how much are the salaries varying? Is a lot of people getting salary in similar ranges, or there is a large amount of variation? What's the maximum salary versus what's the minimum salary in general? How much the CEO earns versus how much the janitor earns effectively? And how is the salary distributed? Usually it's given through skew and kurtosis, which actually tells you how different it is from a normal standard distribution. But let's not go into depth of mathematics over here. Let's just see the visualization first. So a usual normal curve would be something around like this particular form, but this is right-tailed. which means that, hey, on the right side towards the end, there are a lot of data points, and it does not pretty much end here. So a normal distribution would have actually ended up over here, and this would have been the mean. And one of the telltale signs of a right skewed distribution, I would say, is that the median is often behind the mean in general. So one of the large values can actually offset median a lot easily. Then, offset mean a lot easily. Then it could offset median, because median is like if you arrange all of the values in a sorted manner, what's the middlemost value? If the last value is large enough, it won't change the middlemost value, right? But for a mean, it's the average. You actually want to see what are the outliers in this particular case. So one of the methods is called box plot. You can read up about that. It just tells you that, hey, if we make this particular simple box plot, how many data points lie outside. So you can see on the left, there are almost no outliers, but on the right, there are outliers, which can be understandable given the fact that it's the salary distribution. There are some people who get paid immensely well, like maybe the company CEO or top level executive, or your manager's manager who got you the promotion, who you got the promotion. So they are paid pretty well in general. So this is why distribution matters, because now we know that there are some outliers which are not really related to the rule. So if we want to actually predict that did a person leave or not, we need to decide what do we do with the outliers. Should we keep outliers in the same data set? Like, is a person who is just an average employee leaving same as leaving a CEO leaving? A CEO might leave for different reasons altogether. A CEO might not think that, hey, I need a 10% hike, so I'll leave. A normal person might. So this is why outliers matters. You need to understand how and why do they exist, so that you can actually factor in that bias when you are actually making your own model or your own thing in general. So maybe when I said about naive prediction before, one thing which I can introduce is that, hey, forget job satisfaction also. Like if a person is satisfied, obviously they will stay. But there is another factor, that if a person is immensely overpaid, and by that I meant something like paid more than 80% of the people. Let's say that person is not going to leave because, well, he's overpaid. Why would he leave in general? So let's just factor in that particular aspect and see that, hey, how does our naive prediction actually change? So this is when our prediction is getting a bit more refined without even using machine learning. Usually there are two methods to detect outliers. One of them is this IQR method, where you actually make this box plot, and there's a very standard way of doing that. Again, my aim is not to go with the math in this session, just to give you the grasp of thinking and see that which of the points are outside this box plot. These are the outliers. Another is the Z-score method. You plot a normal distribution and see that, hey, these points think like they are not belonging to this distribution. So that's a simple method. Then you can see that I told you this data is right skewed. So whenever you are using it for machine learning models, the problem with that is that they often require data in a normally distributed manner for a lot of algorithms, especially the neural networks. I would say even for the large language model, at the heart there are neural networks. So a lot of processes in there have the assumption of the data being normally distributed. So there might be some transformations you might need to apply. One of the simplest one is the log transformation. Just take the data set and apply a log function on top of it. You can do it with salary because salary is never negative. I mean, I hope not. It won't be negative in general. If it is, there is some problem. No one is actually paying to do the job in general. So obviously clean that up. But yeah, so whenever you apply a log transformation to a value which is very large, it actually shrinks a lot more than a value which is like average. So this is why a log transformation turns this into this, and this looks a lot more like normal distribution, I would say. This looks a lot more like, yeah, this is something which is what we expect to see in a normal distribution. If we are doing any kind of modeling, then yeah, this is something I would like to work on. So think of it as when I said that, hey, salary greater than a particular number, a person is not likely to leave. Why don't we talk in log scales on that particular manner? That might be even better. So that is why the log transformation usually works out. There are different kinds of transformation again. There is my favorite box in general, which actually just finds a curve which is going to make this into this. Like log is just our guess, but box is just going to find a curve which is going to make this into this, quite literally. That's all. One of my favorite statistics I want to look at in general, my first go-to is value counts, not just for the features, also for the targets. This actually tells me that how the data is distributed. Like now I see that a lot of the data comes from the engineering department, and then it's the sales. So more than 50% of the data is made up by these two departments. So that there's a bias over there. I would like to analyze that, hey, how many people from engineering and sales quit on average? So if a lot of people don't quit from engineering and sales, maybe I should have a rule that, hey, if they're from engineering or sales, they are not likely to quit. So this is the kind of analysis which is actually worked out with value counts. So another thing is, when I was talking about ordinal data set, in a lot of modeling problems, you usually give up the numbers. And in some cases, the order of number matters. And we as humans know that 2 is greater than 1, 3 is greater than 2, 4 is greater than 3. So obviously, for us, the ordering makes complete sense. And this is what we have actually taught our algorithms as well in a lot of cases that, hey, 4 is something which is greater than 2 inherently. So if it's an ordinal data set, if there's an ordinal feature, I would say in this particular case, it's satisfaction. So we should keep the order maintained. So if satisfaction was on a scale of low, medium, high, very high, great. We should convert it on a similar scale. We should go from 1, 2, 3, 4, 5. We should not convert it randomly. It should not be that great is mapped to 2 and low is mapped to maybe 5, because that does not respect the order. So we need to analyze data to see that where do we need to respect the order as well. And this is just something which you can actually go about analyzing, that why is there a long tail, is there a long tail or not. When I say right skew distribution, you can see it clearly has a long tail. That's why it is right skew. So this is something you can keep on plotting and analyzing. But yeah, this is what I want to say, that you should always look at the data and ask questions that why is this happening? Because your why actually makes you much sharper on that data set. One thing which you will definitely encounter in most of your data set is that you will have missing data. And you should know what to do about missing data. So broadly, missing data can be categorized into like 3 different types. One would be missing completely at random. Like maybe you floated out a survey and the Google form glitched for a few people randomly. So their data is missing, or some part of their data is missing. There's not a lot you can do about it. You would usually want to either safely drop those features, and if you don't want to drop, so you would just want to put the median or average feature or any kind of feature in that particular manner, that hey, we don't have the data set for them, but it's completely at random. We did not mess up. Another thing would be simply be assuming that this is missing at random, but it's not missing at random. I know this is a bit confusing aspect, but let me give you an example. Maybe you are collecting an income survey in general. Maybe you are getting an income data. You just want to say that with what income do people actually buy a big house in general. So you're less likely to get the income of younger people in general, because younger people have lower income and they don't actually want to report that. So because they don't want to report that, you are getting a missing data in general. So in this particular case, what you would actually want is you should actually keep a column that, hey, that person did not report it. And the last is very obvious, missing not at random at all in general. So in this particular case, missingness actually depends on the missing value itself. That, hey, this value is missing. That means that this person, that's a telltale feature that, hey, maybe this is something which we should look at. That this is very similar to missing at random and missing not at random. They are kind of very confusing and similar. It's very hard to actually decide. But either way, the transformation you do or the thing you do with this is pretty much similar. You actually say that, hey, this particular feature was missing. Let's make a Boolean flag for that, that hey, this feature was missing. We should have this in our data that this feature is missing, because that's something which actually tells us something that because this feature was missing, there might be some reason for it. We might not need to factor it into a prediction. Maybe in this particular case, if salary was asked by people, that hey, everyone was asked their salary, and a lot of people who did not report their salaries also happened to be the ones who left the company. Or maybe a lot of people who do not report their satisfaction also happen to be the ones who leave the company. So missingness is telling you something, that either people are not bothered about filling out those surveys, or maybe people just are so embarrassed that they don't want to report the salaries. So this is why you should have a flag that hey, they did not report it. This is missing. That is the kind of flag we need, because now that actually serves as one of the key features, I would say, which helps you predict. It's like a key clue for you as a detective. It's not just random missing data. So you often want to visualize it as well to get a better hang of why is it missing or not. And you actually want to find correlation of that data with other columns, that hey, if X feature was missing, was a feature Y as well missing. You actually want to find out the correlation with the target column as well, that hey, for the people who are not reporting this kind of data, is the distribution of the target column changing? Like we have what, 75 to 25 kind of imbalance. Like, is the imbalance maintained when the data is missing, or are we saying that hey, no, the imbalance is not maintained, and there is definitely a reason for this particular feature to be missing? And when you find the missing data, you have to obviously most often than not do something about it. You can't really put missing data into machine learning models. Most of them will not work and will throw a random error at you, which is going to leave you scratching your heads in general. So one of the common imputation strategies are either you take a mean, median, or mode, or something like that. Mode is basically the most frequent value, and you just impute it, and you just keep another feature that hey, this particular data was missing. Or you take a very random abstract value, like if salary is missing, just take a number -1 and put that in. Now your model inherently knows that -1 is something totally different out of distribution, so it gets the hang that maybe this was missing. So these are two basic strategies which I usually use in general. There are different as well. You people also go with the imputation via algorithms, that hey, maybe this person is very similar to another person I know in the data set. Let's just impute their values. So that is basically something which is called KNN algorithm, which you use to impute the missing value. You can find them, a lot of implementations of these exist. What you need to understand is when and how to use what. And obviously, as I told you, missingness actually serves as a feature a lot of times. So you actually want to keep a column saying that hey, this particular thing was missing. So in this particular case, mean leave rate when salary was missing is plotted by this particular feature in general. So yeah, that's all from my end. I hope you got an idea of why you need to do EDA and how exactly it helps you think sharper. Now, when I'm going to go into the modeling part, I have a lot of things in my head. These are going to help me decide what model to use. These are going to help me decide what kind of hyperparameters to use. This is going to save a lot of time for me. This is something which might help me decide that, hey, this data is not enough, or this data is not good enough, I need more data. So let's not go into the modeling altogether. Let's go into data collection. This might decide that, hey, this data is pretty good, let's use a big model. So this is what EDA tells me. So I think we are going to open it for Q&A now.
Thank you so much, Bhaiya. That was an incredibly insightful session. And I think one of the biggest takeaways for all of us is that, while tools and models and technologies, they continue to evolve, the ability to truly understand the data, I think it remains a timeless skill. So, and hearing about these ideas from, someone who's working at the forefront of AI, I think it makes these lessons even more valuable. So, now with that, we'll now open the floor to questions. Participants, if you have any questions regarding the session, Bhaiya's experiences, careers in data science, AI, or analytics, feel free to put them in the chat. And we'll be taking questions from the chat only. So we'll try to cover as many relevant questions as possible in the available time. So go ahead and start dropping your questions. So one question is there, Bhaiya. So you've gone from IIT Guwahati classrooms, to working on cutting edge AI systems at Microsoft. So what's one skill that unexpectedly became like far more important in the industry than you thought it would be during your college days?
That one particular skill I would say is making good enough systems quickly. So basically in college, you often have this notion that I should make the best system, and you do a lot of iteration around it that, hey, let's try to increase the accuracy 0.1% on 0.2%. But what matters a lot more than that is that, hey, maybe 90% accuracy is good enough on that task. Our focus should be on making sure that this accuracy is actually realized by a lot bigger people. So I would say making the model scalable and deployable before making it more optimized is something which is I did not realize it in college, but it's pretty useful. And yes, the EDA part in general, I would say, is pretty useful because whenever I look at problems, the perspective I have from EDA helps me the most. I don't usually go with the same pipeline I've shown you because problems are much different, but it's just that this is something which I do in my time, in my first or second day of analyzing a problem, just to see that what I'm going to do in the next 30 days, because this actually decides the course of my action. And obviously, I am a greedy person, so I want to utilize my time for the best possible outcomes in general. So this is one of the easiest ways. So it's like low effort, high reward thing. So that's pretty good.
Yeah, yeah. And I think one question is there. Uh, what was your first exposure to data science or machine learning, and what made you stick with it?
My first exposure to data science or machine learning was, I think, with this platform called Kaggle. So I was in summer analytics. I actually did it, and I got to know about this platform called Kaggle, and I saw a lot of problem statements, and they felt like magic. Like there were cancer detection from images. I know it looks very trivial right now because of AI being the buzzword, but back in 2019, I would say, when I was in my second year, these felt like magic that, hey, you can just give an image and it can tell you have cancer or not. I mean, cancer is solved after that, I guess. It isn't, but still, that felt like magic to me back then. So that was my first exposure, like thinking of myself that I want to be kind of a wizard. I know this is a very weird thought, but yeah, that kind of thinking actually helped me stick with data science a lot more. That, hey, what I do is actually something which a lot of people might not be able to. I mean, a lot of people are, but back then I used to think that. So
Um, one more is that how is AI helping data scientists at Microsoft?
So AI is helping data scientists at Microsoft in broadly two manners. One, it is making them a lot more productive. So the core problem with data science in a lot of areas is that it is very, very fast. Like you learn a concept and it becomes obsolete in like 2 months. So that's one of the problems. So you have to be updated with learning and you have to do it really quickly. And using AI to learn faster is something which I have actually adopted in my workflows in general as well. Like usually I maintain my own GitHub of resources and all. I can share if you want. That is something which I keep on updating. So that's where AI is helping me in first place. Second place is it has actually offloaded a lot of tedious work, and I actually happen to do more of a thinking and judgment work. So whatever you have seen in the notebook, it's obviously not written down by me. Every line of it is not down by me. I just gave them the idea. I just usually got that, hey, this is what we should do. So the idea I had was that, hey, we should actually plot these things. I'm not writing the code in general. That makes me a lot more efficient. So my brain is more reserved for the thinking part, and AI is more reserved for the actual coding it out part, because when you are clear with your thinking, AI can code it out pretty well.
And since we also have a lot of students here who are just starting out in AI and ML, I have to ask, what's one thing you believed about data science, like during your first year or second year, that turned out to be like completely wrong?
So one thing which I believed in general about data science and AIML was that you actually need to be PhD experts to get ahead in industry. This turned out to be pretty wrong. And I think this turned out to be wrong because of the timing in general. I think I was right back then because people were hiring a lot more PhDs and master students. But it's just that the sheer pace at which industry is evolved, most of the employers actually care about your ability to get the work done. That's all. That's all they care about, because PhDs and masters, I think, have a bit of backseat because they are usually stuck in academic environments that they have their other pressures in general. So they are a bit out of industry for a lot of time. And you don't really want to get out of industry right now. So I would say as long as you can make impressive projects right now, you can actually convert a lot of opportunities and you can go ahead and advance in your career. So the rhetoric is becoming more and more towards that you don't even need a PhD or master's anymore to get into data science. But I had this notion because when I was in college in 2019 in IIT Guwahati, it's an IIT, you would expect a lot of companies to come and hire, but I think only 2 or 3 companies used to come for data science profile. So being a data scientist back then was a gamble. Like not learning SD was something which was a pure gamble back then. But as of now, I don't think it's a gamble. I think if you are confident that and you like the field enough, you can go ahead with that.
Okay. One question is there. What is the best way to learn mathematics for ML?
Best way to learn mathematics for ML is start learning about the end problems first. That hey, this is what I want to build, and then start going into a layer deeper. That this is how I want to build it. So maybe a layer deeper right now might be using a coding agent to actually solve a lot of these things. That hey, I have this idea. Can you code this out for me? And then when you realize that hey, it does not work because it does not a lot of times. You try and debugging, you try and learning libraries. And when you learn libraries, you realize that, hey, I don't understand a lot of things and I might need mathematics for it. That is when you start learning mathematics because now you have an aim in your head that I wanted to do this project, I wanted to solve this problem. And mathematics is needed here. So instead of abstractly learning linear algebra, I would say learning it in this particular sense is much better because when you do this, you realize that you are reading about different models, loss functions. I'm not sure if people are comfortable with this terminology right now, but you would come across things which require mathematics. And when you encounter them, you would have a stronger motivation to learn mathematics. So don't get into the math at the start. This is something which I would suggest because even I did not get good grades in linear algebra in my first year. I think there was a course I got horrible grades over there. But by the end of my fourth year, because I was so invested in machine learning, I think I was one of the top guys for linear algebra on campus because I studied a couple of books for linear algebra just to understand how a lot of things work. But that was because I was severely motivated by it.
Definitely. I think we can end now. So thank you once again, Bhaiya, for such a wonderful session. It was fascinating to hear your perspective on EDA and like learn from your experiences from your days at IIT Guwahati and to your current work at Microsoft. And I'm sure everyone here will also leave with not only a better understanding of EDA but also a clearer picture of how these foundation skills they still continue to matter even as AI becomes increasingly advanced. And of course, thank you to all the participants for joining us today and making these sessions worthwhile through your enthusiasm and engagement. Before everyone leaves, one last reminder: the week one quiz closes today at 11:59 p.m. Indian Standard Time. So please make sure you have attempted it before the deadline. And that's all from our side. Have a wonderful evening. Keep learning, keep exploring, and we'll see you in the next Summer Analytics session. This is your host, Bhavish Negi, signing off.
Okay. One thing I would like to just add, I think, is it over or not? Did we close it? Yeah. So one thing I want to say is that I'll share the notebook and the GitHub with you. And you can share it with the participants because I see a lot of those comments in chat. So please do share them. Okay. And thank you for having me here. It was a pleasure interacting with you folks.
Definitely.